I'm Paola. I'm currently working as lab developer at Birkbeck College in London. And my main expertise is mainly in using fNIRS for cognitive neuroscience experiments, particularly in adults. But lately, I've started to explore its use on toddlers from 3 to 5 years old. So today, in our webinar, we will discuss the methodological aspects of using fNIRS for cognitive neuroscience experiments. And in particular, we will talk about the main stages of an experiment as presented in this pipeline over here, and with a particular focus on neurodevelopmental studies. So we will first give an overview of all these various stages, and we will then see these applied to real fNIRS data recorded on infants and toddlers. Of course, it is worth mentioning that within this framework, there are still a lot of open issues and questions in the fNIRS field, like these ones, just to mention a few. And this particularly concerns the lack of standardized methodological procedures. So we don't have any standards yet in terms of data analysis or experimental approaches. And also we very often have a lack of methodological information in research papers. And this can also be a little bit more complicated for neurodevelopmental applications where there is still a lot of ongoing work and new developments are needed. So what we will present today are the pipelines and the approaches that we've been using so far, and that are the results of many years of work in our respective labs. So we'll leave it to Renata now. Renata?
Yeah, sorry, that wasn't working for a second. Okay. I'm back. Okay, hi everyone. Thanks Daphne for the lovely introduction and Paola for the outline. So I'm going to talk about experimental design. So the first step that you need to do actually when you design your own study. So the first thing that you need to consider is age and ROI, so the region of interest. And that is important because, well, what is your question? So you need to understand where exactly to place the optodes, and you need to remember that the brain develops very rapidly from the womb, starting from the womb and then until adulthood. And especially in the first few years of life, this development is very rapid and the brain forms in a very high speed in these years. So that's the first question that you need to address yourself. Then an important thing is to consider when you do an experimental design as well is to measure exactly how the cap fits the infant head, and you be consistent in the placement of these optodes across all the participants you have. Here you have an example, and this is taken from a study from Sarah Lloyd-Fox in the UK, in London, at the Birkbeck College. And what they did is to take as point of measurement, or let's say the reference point, a 1020 system from the EEG system, and basically replace the same cap in the same method, so you will be consistent across infants. And that's very important, because if you don't keep such consistency, then you might measure, you might have more chances to measure different areas from different babies. So that's one thing to remember. Another thing to remember actually is, where do I put, so a question that you should ask yourself, where do I put the head cap? Where is my ROI? But also, which head cap am I using? There are different head caps. And what I mean by that is, for instance, you see here, in the first yellow figure here, you see that the SD separation varies. The SD is the source detector separation, or sometimes called also transmitter and receiver. So the more far apart are these sensors or optodes, the more in depth you are measuring in the brain. And in this case, the head caps will increase in size over due to head circumference. So it won't be stable for all the babies you're measuring. So that means that the depth of measurements will vary as well across infants. So it's something that you need to consider before you start your task or your experiment, designing your experiment. Another thing to consider, well, another setup that you can use is a structured array. In this case, the separation of source and detector, or transmitter and receiver, is fixed. So regardless of the circumference that you have of a baby, the distance will be stable. That means that the depth of measurement in the brain is going to be the same, is going to be equal. So these are some considerations. Other things that you need to think about always, where to put the optodes, is actually what is your ROI and where exactly are you going to put your optodes if you don't have an fMRI. So in an ideal world, you will have for each baby an fMRI data set that you can check exactly where the location of your brain area of interest is, but that's not always the case. So what do? One way to deal with this is to check previous literature and see whether they can guide you in understanding where for each age group you should put the optodes. Here are some examples. So here there is a study from Lloyd Fox and colleagues from 2014, a co-registration study with fMRI and fNIRS, and they show you the exact location of some of the frontal, prefrontal, and temporal location, but also more frontal here, so from 4 to 7 month olds. This is an example, but you also could see for younger, there is an EEG paper published in 2014 that also gives you some sense of the 1020 system locations that you can also use as a reference point. But still, research, as Paola said, is ongoing, so still atlases are being created at this moment. Then that's one of the other things you do, or maybe one of the first in this step, is the task design. You need to design your task, and the best way to do it is to read a lot of literature and see what similar papers or similar work used. There are 3 task designs that are often seen in fNIRS: the block design, even related design, and mixed models. The most used in infantile list of fNIRS is block design. So what do we see in block designs? Typically is experimental condition followed and preceded by baseline conditions blocks. And within each step, each condition, you will have, you could present more than one stimulus. So for instance, you have a peekaboo face, it might be just one video, or it might be several times one image, for instance. And this design has pros and cons. So the pro is that it has a strong and reliable signal, but the cons is that the effects of individual stimuli. So as I said, if you have more than one stimulus in one experimental condition, let's say in trial 1, then you cannot actually isolate the effect of one stimulus, but the end result will be one hemodynamic response evoked by all of this stimuli. And another con is that responses to entire block might actually include effects are related to the processing of the stimuli, for instance, sustained attention or task-related processing. So things that I want to point out that you need to remember when designing a block design is to really consider the experimental and the baseline trials. So first, the content. The experimental trial should always elicit a response from your region of interest. At the same time, your baseline condition, your baseline trial, in adults, typically, if you have like a visual task is like a blank screen or something. With infants, this doesn't work. Most of the times they're gonna start crying. So you need a baseline trial that does not elicit a response from your ROI, or at least a lower one compared to the experimental trial. The length. So the length of the trial, how long should be my trial? Well, the experimental trial should be long enough to elicit a response from your ROI, and the baseline trial should be long enough to allow the HRF, or the hemodynamic response, to go back to baseline, basically to return to a baseline level. Attention, that's something very important. You need to keep your participant attentive. And that's not easy thing to do. If your protocol is the first time you try it, it's good to try it and to pilot it. It's very difficult to know the response of a baby. So other things for this type of design is how many stimuli do I present? Well, you need to present enough, that's a balance, so enough stimuli to maximize the signal to noise ratio, but also you want to avoid habituation effect, so not too many. You can, as I said before, just check the literature. If there are some studies on habituations also in infants, so you can also see some information on this there. Other things is the physiological oscillation, basically the anticipation onset of stimuli. How do you avoid it? You need to, one way is to jitter the onset of the experimental trials or stimuli, or you can choose an event related design. That's also a possibility. Order representation is also important. So the trial sequence, as I said, it is good if you always start and end with a baseline trial. So you have baseline, experimental trial, and baseline trial again. So then you have the same baseline follow your trials. But also, is your task part of multiple sessions? That's very important, because if your first task of, let's say, 3 tasks is on face processing, and you show a lot of faces, and your second task is also about face processing, you might have habituation also there. So really consider how your testing day is going to be. Now I move rapidly to the event-related design. This is, I saw this more in auditory contexts, but what is actually shown is that the single stimuli are presented in a faster way compared to the block design, and if there is a long interstimulus interval after the stimuli presentation, then it actually you actually have more trials than in a block design. The pros of this task design is that the hemodynamic responses to single stimuli, this time you can detect them, you can estimate them, and you can disentangle task or attention related biases. The cons is that the signal obtained from infant data is actually weaker compared to block design, and that's the main reason why I guess we use in infant studies the block design, which is very important. There is also the mixed model. So these models, they try to take advantage of the positive characteristics of both previous designs, the block and event related. And what happens is, what is shown is typically single stimuli at a random time intervals and relatively short interstimulus intervals. And the stimulation periods are intermixed with control condition as well, but there are less examples on this. Task design really depend on your question. So really take your time to define your task, because this is the step you cannot change. Pre-processing and statistical analysis you can always play around with, but the task design is something that stays there. So it's a really important step. So then you move to data acquisition. So that's your second step. So you have your task done. You set up the experimental design. So what do you need to consider in your lab? Well, as a first point, I would say do not test alone. It is possible, I've done it, but you never know what's going to happen. So you might need another pair of hands with you. The babies are always unpredictable, so you might need somebody else to distract them or attract their attention while you are figuring out some problems with the computers or anything. It's better to test in 2. So I would suggest that for you. And then avoid distractions in the lab. That's also important, because if you have something that is more attractive to the baby than your task, well, that's a problem. You should instruct and engage the parents. That's very important. Sometimes babies just feel parents' emotions, but also the parents should be comfortable in your lab. So give them all the information they need. Take out measurements, as I said at the beginning, and also pictures, also from parents. Is sometimes funny for them to come back home and have a picture of their baby being a little scientist. Keep the baby busy, happy until the task starts. That's very important, because if they don't like the setting, they're not gonna do your task for sure. So try to keep them relaxed and happy. Make sure the head cap is well placed and tight. So the optodes need to be in a good position. So if you have time, and that you never know, but depends on the behavior of the baby, then try to also, I'm going to this point, to adjust the optode if you have time, and make the as much as you can ensure yourself that the head cap is well placed. Record relevant behavior information. So NIRS is not the only measure you might need. So you might also need to know whether the baby is looking at your simulate or is looking somewhere else. So that's an important information to take, and this depends entirely on your task. And then, well, start your task. So that's the main, the last step, let's say. Next is, how do I evaluate my study design? Is it good enough? Well, you should pilot if your task was not done before. It's good to see how the data look like. So do you see the effect expected in the region that you thought they would pop up, and how is the response to the baseline trials? Look also at the individual data. Is the variability across infants really big or not? And is there habituation? How is the baby's behavior is also very important. As I said, you never know whether maybe they're too bored and you need to do something about it. So it's good to evaluate all these parts after your first piloting. Next, we move to data pre-processing, and I leave the floor to Paola.
Thank you, Renata. So great. So once we have collected our fNIRS data, we start from our raw intensity signals. So we have signals measured at 2 or more wavelengths that include noise and various components that we want to minimize as much as we can, so that we get to a cleaner version of our concentration signals, so a cleaner version of oxy, hemoglobin, and deoxyhemoglobin signals that will allow us to extract meaningful information to run our statistical analysis. So we need to first apply a few pre-processing steps to remove unwanted noisy components and improve the statistical inference step. So here on the right, I've included a general pipeline that I typically use on my own data. So I usually start from a visual inspection of my raw intensity data. And typically I do this to identify noisy channels, what type of noise I have in my data, if there was any saturation of any channels that has to be excluded. And this step is also very useful because it can help us to identify, for example, which type of motion we usually see in our data set, so that we can plan our next steps accordingly. In terms of pre-processing steps, I usually correct for head movements and use bandpass filter to minimize physiological noise. And then at the end, I convert into concentration changes of oxy and deoxyhemoglobin that I use for my stats. So let's now have a quick look at what type of noise we can find in our fNIRS data. So I divided these in 3 main categories. So measurement noise, physiological noise, and motion artifacts. In terms of measurement noise, this can arise from, for example, a poor optical coupling. So this means that we don't have a good contact between the optodes tips and the scalp and the participant's head. So what can happen is that we are not measuring anything physiologically meaningful, for example. So here on panel A, I'm presenting an example of oxy in red and deoxyhemoglobin signal in blue, recording from a channel with a poor optical coupling. So it's already clearly visible that this signal is very noisy. And in particular, if we look at the signals in the frequency domain, we see that the power spectrum resembles very closely the power spectrum of white noise, with a constant spectrum across the whole frequency bandwidth of the signal. So in this case, we want to make sure that during our data collection steps, we try to minimize as much as possible the coupling, but this of course becomes very difficult for infants. Then we can have channels with detectors saturating because they're receiving too much light. For example, if there is too much ambient light. So what we get, an example of what we can get is shown in panel B here, where we have just flat lines because the detectors basically stopped working. Finally, we can have instrumental noise, or noise coming from the hardware, such as thermal noise inside the instrument. These can be seen as low drifts in the data, so like linear, very low frequency trends in our signals, but these can be easily removed by using detrending or high-pass filters. In terms of physiological noise, so noise of physiological origin in our fNIRS data, I'm starting from one of my favorite figures from the paper by Taxidis and Schalkman. So here on the left, you basically see what ideally we want to measure with fNIRS. That is the hemodynamic response that follows neuronal activity that is evoked by our cognitive task. But in reality, what we get, so our fNIRS signal is actually a mixture of a lot of other components that can be both of neuronal and systemic origin, and can also be spontaneous or elicited by our cognitive task, coming from both the cerebral compartment and the extracerebral compartment of the head. So with the preprocessing, what we want to do is basically to minimize all these components and maximize the hemodynamic changes. So our task evoked hemodynamic changes. So this is a very broad topic, and I will not have the time to discuss this in depth today, but I've included here a couple of very interesting papers on this topic. So a useful tool to look at the physiological components in our fNIRS data is to look at the signals in the frequency domain, for example. So here I'm showing an example of an adult fNIRS signal, red being oxyhemoglobin, blue being deoxyhemoglobin, recording during a simple block design experiment with 20 seconds rest blocks and 20 seconds task blocks. So if we convert our signal from the time domain to the frequency domain, for example, using Fourier transform or computing the power spectral density, we can assess the main physiological components that we should be seeing in our fNIRS signal. So it's very clear usually to see the heart rate peak that is between 1.5 hertz for adults, while for infants and toddlers is a little bit higher, between 2.5 hertz. We can see our breathing rate, our Meyer waves, but also our stimulation frequency. So the hemodynamic component, basically our hemodynamic response component related to our task. And this tool can be also useful to assess the quality of our fNIRS channels, especially looking at the heartbeat rate. In fact, if we have a good channel, it means that we have like a good coupling between our optodes and the scalp. So in that case, we should be able to see the heart rate component both in the time domain, as shown here, with faster modulations, especially in our oxyhemoglobin signal, with a period of around 0.8 seconds, 1 second for adults, and also in the frequency domain, where we observe a clear peak in the heart rate range. So this is also true for infants and toddlers, but shifted to higher frequencies. Whereas where we don't have as much good optical coupling as in the case on the left, what we get is a noisy signal with a flat spectrum where we cannot identify any of the main physiological components of the fNIRS data. So this can be roughly an indicator that can inform us on the quality of the fNIRS signals that we have recorded. So there are different tools available that we can use to minimize this physiological noise. For example, very popular ones are the use of short separation channels to remove the scalp component from our fNIRS channels, or also monitoring additional physiological parameters alongside fNIRS, that can be regressed out from our signals. But these, of course, require additional hardware. So one of the most common and most basic methods that people use to at least reduce the very low frequencies and the higher frequencies in the data is to use bandpass filters. So a filter is just a mathematical operator that allows some frequencies to pass, called passband, identified by a cutoff frequency range. So we have a lower cutoff frequency and a higher cutoff frequency. So the frequencies in between will be preserved, while at the same time we will be removing the frequencies above and below our cutoff frequency range. So when designing a bandpass filter, we want to make sure that our stimulation frequency, so the frequency of our experimental task, is included in the passband. Otherwise, we will be removing important components, our hemodynamic response, from the data. So we'll show you now a couple of examples about what happens if we exclude our stimulation frequency. So the first one is an example from an adult data set, recording during a visual cortex stimulation with 20 seconds task blocks, spaced by 20 seconds rest blocks. So here on the left, you will see in black the original unfiltered oxy and deoxy hemoglobin signals, while in red and blue, you'll see the resulting filtered oxy and deoxy. So here on panel A, the cutoff frequency range is appropriate and includes our stimulation frequency. So here the resulting signals are actually, we basically have removed the very low frequencies, so all these slow modulations in our signals, and also the higher frequency noise like the heartbeat rate. So our oxy and deoxy signals look cleaner. We have preserved the task-related modulations in the data, and the changes have an appropriate amplitude, around 1 micromolar or so, across all our experimental blocks. Whereas if our cutoff frequency is too narrow and does not include the stimulation frequency, what we get is a very weird version of oxy and deoxy with strongly attenuated amplitude, and this can impact our statistical analysis, as we can have false negatives at the group level. So below I'm showing another example. In this case, these are data set recorded on toddlers during a block design experiment with 20 seconds task blocks and 20 seconds rest blocks. So here I'm showing the block averaged hemodynamic responses. So my oxy and deoxy averaged across my trials, basically. So here on the left is the result of my block average hemodynamic response, where I filter my data using an appropriate passband, which includes my simulation frequency. What we get is a very nice hemodynamic response with a nice increase in oxyhemoglobin, nice decrease and anticorrelated decrease in deoxyhemoglobin. While if my cutoff frequency range is too narrow and does not include my simulation frequency, we get this dashed line version of oxy and deoxy that you can see have a very different shape and a much lower amplitude. So in this case, we risk of having false negatives at the statistical inference stage. So we need to make sure that our cutoff frequency range is chosen properly. So in terms of motion artifacts, I will leave it to Renata, who is the expert within this topic.
Thanks, Paola. So yeah, we move to motion artifacts, and yeah, it's nice that, Paola, you mentioned how important it is to define your bandpass. So any kind of filtering, so also how you deal with motion artifacts is important because they affect your data. So motion artifacts arise from relative movement. So the optode moves, when the optode moves on the skein, so when there is decoupling between the optodes and the scalp, as Paola said, versus general movement. So if the baby is moving the head, it might not impact your data if the cap is tight enough. Motion artifacts are characterized by a positive correlation between oxy and deoxyhemoglobin. And there are different types of artifacts that you can see in the data. So you might have like fast spikes or step changes, baseline shifts, or slow drifts. And the slow drifts are actually are harder to distinguish from physiological changes. Sorry, I would go on. Okay, so the best way to deal with them is to avoid recording them. Yeah, it seems stupid, but yeah, it's the best way. So if you, there are some things you can make sure while you're testing to try to avoid to record these kind of motion artifacts. So the first thing, as I said, is making sure that the headgear or the head cap is tight enough and well positioned on the infant head, and try to minimize or balance the weight of the fibers or the cables on the infant head. For instance, I had a paradigm where the infant was wearing only cables on the right hemisphere. So I didn't put them hanging on this way, otherwise, yeah, the coupling will be super easy. So you need to find the right balance. You can bundle the fibers and the cables to ensure the stability of the cables. You can protect the cables from being grabbed. This doesn't happen, I guess, with adults, but with babies, it is such an easy movement, and it is always good to think about this. And you need to think whether motion is part of your task. If you need a response from your participant, think about this, and keep the baby interested and attentive to your task. Again, like I'm stressing this point, but it is very important. Then, well, you recorded the data and you have the data with motion artifacts. That's for almost always with babies. So what do? So you can detect your motions. There are two ways. You can visually inspect the data. And the problem is that this is not reliable. This is totally subjective. And if you don't the experience with fNIRS is also very hard. And even if you have experience, it's very time consuming. What if you have 100 babies? It's very time consuming. You cannot do it for every channel and every baby. So there are other ways you can do this. I use personally Homer 2. Now, well, there is also Homer 3, but there are other softwares available that use automatic motion artifact detection. And in Homer 2, for instance, motion are detected channel-wise, and those are changes in optical density when they exceeds a certain amplitude threshold over a time window, and the motion that is identified also exceed a certain standard deviation threshold. So there are many thresholds to be exceeded once to define a motion artifact. So you can play around with this and identify the real motion artifacts in your data. And this is more reliable and easier to reproduce for other researchers as well. Then you should correct for motion artifacts. So what do we do? So there are different methods available at the moment, and here you have a list of some. So for instance, spline interpolation, wavelet, principal component analysis, etc. And there have been papers comparing the efficacy of these different methods on adults and children data as well as infants. I think with infants there were only 2 at the moment. And some of those papers, they combine different approaches. So why combining different approaches is because different correction methods have a different way of tackling motion artifacts, and combining 2 different methods might help cleaning better the data. So for what is optimal for infant data? So as I said, there were only 2 papers on infant data motion artifact correction, and I'm gonna show you the one, actually the one I wrote with Laura Pirazzoli and other collaborators about infant data. And what we did is to suggest the use of spline in combination with wavelet filtering for infant data. So why did we choose these 2? Is because mainly these 2 methods have been, they target differently motion artifacts, and they have been suggested for adult data. But I'm going to tell you a little bit about how they work singularly. So wavelet filtering is a more general correction method. What do I mean by general? I mean that it works or it acts on the entire time course, on a general time course, basically. And it decomposes the entire signal in wavelet coefficients. After that, he removes the coefficients that are mostly likely associated with motion artifacts. So here you have an example. And what you see is the unfiltered data. So before the removal is the blue. So you see a lot of artifacts in the all-time course, and then after the removal. So once you, here in the Wavelet, you set up the IQR, so the interquartile range. This, the Wavelet has not been only suggested for adult data, but also by Hu and colleagues for children, toddlers, and by Barrett and colleagues for infant as well. So that's one of the main reasons why we include it in our combination. Spline interpolation is a different method, and I would call it like a very specific method. Why? Is because it works on a specific bit of your time, of your signal. So first you need another function actually to identify the motion artifacts, is the one that I mentioned before. So the motion artifact detection. So this is your signal with a big spike and a step change. This is a motion artifact, and you know it. So what you do is first you need to select this, and that's this step. And then this is very simply put, so it's a bit more complex the algorithm than this, but what it does is basically to apply a quadratic spline interpolation and just recreate and put down to baseline this part of the signal and have a clean signal as well. So our idea was that combining these two would cover most of the artifacts that we see in infant data, which are much more noisier than adult data. So what we did first is to compare actually our combinations of spline and wavelet with the performance of all the other correction methods available. And what we did is to test this on real infant data collected with a paradigm of resting state. And this resting state, within this resting state data, we applied a simulated HRF, actually 3 types of simulated HRFs. As you can see, they simulated different types of designs that you could acquire data from. And the simulated HRF here is the gray line. You see it's super smooth. So this is the simulated HRF that we put in this resting state data from infants. And then we applied all the different pipelines containing either only one type of correction method or the combination. So here you see in different colors the different type of pipelines that we applied. And then using the RMSE, which stands for hemodynamic recovery, response recovery error between the true HRF, so the simulated one, and the HRF that resulted from each pipeline, we understood which one was actually recovering better the true HRF. Okay, so the goal of your pipeline is to as best as possible match this line. And what we see from the RMSE is exactly what we see in these figures. So first of all, it's very important to see that rejection, which is rejecting trials that contain artifacts, actually do not resemble your true HRF, but kind of, in this case, increase drastically the response. So this is very bad. And the reason why we stress this in our paper is because this is one of the most used technique for dealing with motion artifacts. So one of our points was, please do consider and do correct your data for motion artifacts. The second thing to see was that spline combined with wavelet, so the red line, is the best estimating the true HRF. You see it's pretty close here, but also in the other designs. Wavelet also seems, so that's the green one, seems to do good also in these 2 designs, a bit less on this one. So I'm not going to go through all of them, but as you can see, the combination works quite well, very well on the infant data. So next we wanted to see how well the combination of spline and wavelet works with real cognitive data. So we tested this on 3 different data sets from different designs and different labs. And I'm going to show you just one of the tasks that we tested these pipelines on. And this is one is my task, basically the one I collected in Utrecht. And very briefly, this is the design. So I recorded hemodynamic activity from 5-month-olds from the right hemisphere. This was my headband. And you have in red sources and detectors in blue, so, or transmitter and the receivers. And this is basically the scheme of the opto template. And these were my regions of interest. So my 3 sets of optodes where I was interested to see whether my hemodynamic activity would pop up or were activated by my task. Task was a task design, and I had 10 seconds of baseline followed by 5 seconds of experimental trials. And I wanted to see whether infants at this age were able to discriminate between phases and non-phases and between different emotions. So what we did is to, once we recorded the data and run the 3 pipelines in this case, to see whether the variability, well, I'm gonna tell you a little bit better, but the variability in single trial and average trials decreased compared when we do not correct for motion artifacts. So what we looked is 2 metrics specifically. One is the within standard deviation at, here I show you only the oxygenated hemoglobin, but the same results all for the deoxy. And we compared for the within standard deviation, we compared for each participant the mean standard deviation of the single trial HRF or hemodynamic response within across channels and conditions. And we compared the standard deviation between the effects that we obtained from spline versus no correction, between wavelet and correction, and the combination of the 2 and no correction. The assumption here is that the lower is the standard deviation, the better is the correction method, because most of the variabilities within participant will be due to motion artifacts. So what we see here is that spline does not work well, sorry, while the combination of the 2 and wavelet seem to do the best job here. And no correction, I should mention, that is when you do not correct for artifacts and you have all the noise in. Sorry. Then we move to the between standard deviation metric. And here we were interested to see whether the variability between participant actually was decreased due to the processing pipeline used. And what we see is that the spline and wavelet were the best in reducing such variability. Again, the assumption here is that most of the variability would be due to motion artifacts. And what we see is that basically, looking at the first set of data that I show you on the simulated data set and a real cognitive data set, the combination of spline and wavelet seems to work better than when you take them alone. So I want to show you what happened to really my data when I applied one of these processing stream alone and in combination. So, so this you see responses to fearful faces. So faces expressing fear. And I applied only spline here. What you see is all the channels I had, and D stands for detector and S stands for source, and here you have all the channels. These are more occipital, temporal, and frontal channels. And so yes, when you test infants, you don't have such a clean data as Paola showed for the adult data. So that's first. But what you see here is a lot of noise. And one thing I should mention is that these black lines are 5 seconds. They just mark time, and is this is time 0. So when I present the stimuli, and then you have every 5 seconds another line. Then I show you what happens when I only use wavelet. And this is very different. So what I see here is that scale is the same. I use the same type of scale for both images, and the signal is smoothed a lot. I should mention oxy is in red, blue is deoxy, and green is the total hemoglobin. So yeah, it's smoothed a lot, and we have a very different scenario here. So if you do a t-test between the your baseline and your activation, probably there is no activation here while there is here. So what is the right one? Eventually our paper, as I showed you, it indicates that spline and wavelet together actually are the best approximating the true HRF. So once I apply the both of them, this is what happens. So I think here I have activity or activation. So it's kind of confirmed that this was too smoothing and this was too noisy. And also it seems a bit cleaner, and also see that actually here there was something going on. But this pipeline didn't allow me to see that. So it's very important that you try on your data and you evaluate how much noise and which kind of artifacts you have in your data. Another metric that we use in the paper of comparison between motion artifacts to correction is to see how many trials survived the correction. What you see here is when rejection was used. So when you reject trials because they have an artifact, when you use only spline, only wavelet, or the combination, and these are the three data sets, the real cognitive data sets that we use. What we see is that the combination of spline and wavelet kind of saved all of the trials, or most of them, for this data set, which is very important for your statistical analysis as well, and for your power, but also for the reliability of your data. So the conclusion of our paper is that the spline and wavelet combined approach is optimal for infant data pre-processing. However, remember that spline requires a prior motion detection step, and that's very, it's tricky. So you need to have a bit of, you need to spend a little bit of time of tuning this one and be sure that you are detecting as much as possible all the artifacts in your data. Wavelet also seems to work well in infant data, at least what I show you in the first data set of the semi-simulated data set. And the good thing is that it doesn't require prior motion detection, so it's easier and faster to use. However, there is no single use for all. So you need to to look at your data, spend time, look at the artifacts and try. One last thing that I want to show you, this is the response to happy faces, to faces expressing happiness. And this is the use of wavelet with different IQR, interquartile range. This is the thing you can set up in Homer too, so what you can tweak. And I use different IQRs. So this is the IQR 0.5 and 0.8. This was the one that was approved, because we tested also different IQR in that paper. And what we see is that the 0.5 actually smooths down my responses and kind of cancel this one. Why is that? This is related to what Paola was saying before about the Bandpass filter. Basically, I canceled, or I cut down I was too close to the presentation timing of my response, of my block design. So you need to really take your time and evaluate your pipeline. So I think now I move the ball to Paola.
Thank you, Renata, for this. All right, so far we've seen what are the main pre-processing steps that we usually apply to our data. So now we are at the point where we got a cleaner version of oxy and deoxyhemoglobin signals. So what we want to do next is finally to localize where functional activity happens. So what we want to do is to run our statistical test our hypotheses, and finally conclude where functional activity happens in response to our particular task. So for the fNIRS analysis, there are two main approaches that are typically used. So the block averaging technique, that is basically what Renata has been showing so far, and also the general linear model. So in terms of the block averaging method, so this is quite a straightforward approach to use, and it basically consists on averaging parts of our fNIRS signals across trials repetitions, so that we get our block averaged hemodynamic response, as shown in the figure here, where we basically get an average oxy and deoxy response to our functional task. So as I said, this method is quite easy to use. Also, it is very common for infants and toddlers data analysis because you don't have to make any a priori assumption on the shape of the hemodynamic response. This is very useful because we don't have this information for infants yet. But however, we basically restrict the analysis to a shorter version of the fNIRS signal instead of using the whole time series for our hypothesis testing. So to look more in depth at how these methods work, let's start from an example of oxy and the oxyhemoglobin signal recording on the occipital cortex during a visual stimulation task with a flashing checkerboard indicated here by the gray bars. So what we do for the block averaging method is that we take our individual trials, we average them together, and we get our average hemodynamic response for oxy and the oxy. So next, to run our stats, we need to extract some parameter that describe these curves, basically, so that are indicator of the strength and level of activity in our signals. So we can choose different parameters. You can choose the peak of the response, a median value within a time window. You can choose the area under the curve. You can use many different parameters for this. What I typically like to use for my own data is the peak of the response. So I basically look for the maximum increase of oxyhemoglobin and the maximum decrease in the oxyhemoglobin. And I use these values as my dependent variable for my statistical test. And I repeat this procedure for each one of my channels and each one of my participants. And then I run a channel-wise t-test or ANOVA based on your particular hypothesis to identify which brain region is active at the group level. So again, my t-value or f-value. So where the channels where I get a significant difference are marked as, of course, active. And I use this information to localize the brain region that shows significant activation to my particular task. Of course, it's worth noting that channel-wise analysis assume that the channel's positions are consistent across all the participants. So that, for example, channel 1 probes the same brain region across all my participants, because I need to group together channels that are anatomically homogeneous in each other. In terms of the general linear model, very quickly, so this is a very widely used method for functional MRI data analysis, but was also extended to the analysis of fNIRS data. So what we do with the GLM is that we first create our activation model, here shown in black in the figure below. And this one represents how theoretically our hemodynamic response, our fNIRS signal should look like in response to our cognitive task. So this is also called regressor and will be part of the design metrics in the GLM. What we do next is that we fit this model to our fNIRS data, and we look at how similar our oxy and the oxyhemoglobin are respect to the model. So this similarity, let's say, it's described by the beta values. So we estimate these beta values that indicates how well the fNIRS signal is similar to the model. So the higher the beta value, the higher is the probability of having significant brain activation. So this method presents the advantage of using the whole fNIRS time series. So we take advantage of the higher sampling rate of fNIRS and its higher temporal resolution. But in order to create this activation model, we need to make an assumption on the shape of the hemodynamic response. So this is mainly for the canonical GLM type of analysis. And unfortunately, this is really not known for infants. So this method up until now is mostly used for adult data set. So in this case, our dependent variable that we will use to run the second level, so the group level analysis, are the beta values. So we, again, estimate the beta values for each one of our participants across all the channels. And again, we can run channel-wise t-tests or ANOVAs based on hypothesis and localize where significant brain activity happens. And also in this case, of course, channel locations needs to be consistent across all the participants. Right, so this concludes the first part of the webinar. Now we will quickly show you one of our most recent study that we've done over at Birkbeck, and you will see the steps that we discussed so far applied to real fNIRS data. So this is one of the very recent study that I've done at Birkbeck with Chiara Bulgarelli, Luisa, and my other colleagues from UCL and Birkbeck, where we use fNIRS to look at functional brain activity in toddlers from 3 to 5 years old. So the data I'm going to present you today are unpublished and just preliminary because we had to interrupt our testing due to the current situation with the virus. But in general, we had two main goals for this study. So the first one was actually to assess the feasibility of wireless and wearable fNIRS for use on toddlers. And that's because we are about to open a new toddler lab at Birkbeck, where we will have toddlers moving around in an immersive VR space, in a cave, while at the same time, we will monitor their behavior and brain activity using wearable sensors. So we wanted to see how well tolerated was wireless fNIRS on toddlers, what are the challenges, what we need to take into consideration before starting our next experiments. But of course, we also wanted to continue along the long history of studies that have been carried out over the years at Birkbeck and at the Baby Lab, in particular to look at cortical specialization to social cues across infancy. So here we wanted to extend the investigation up to 5 years old and see if there is like a developmental trajectory also across toddlerhood. So today I will mainly focus on the first goal, so on aim 1, because we don't have a complete data set yet, so we cannot draw any conclusions about let's say the neuroscience part of the project. So we'll mainly discuss the methodological aspects and give you my impression on the overall feasibility of wireless fNIRS. So for this study, we first wanted to use a cognitive task that was robust and reliable. So for this reason, we used the famous social versus non-social task that was used for many years and many different studies at Birkbeck across many different age ranges from a few months old up to 2 years old. And this task is also quite robust and gives quite localized activation. So we thought it was a good candidate for a feasibility test of our new piece of equipment. So very briefly, the experiment consisted of social and non-social stimuli in a block design, arranged in a block design manner. We had both visual social and non-social stimuli, and also auditory social and non-social stimuli. In terms of the data acquisition and data collection, we recorded data so far on 43 toddlers in total, divided into 3 age ranges, so 3, 4, and 5 years old. We have recorded fNIRS data using the Bright24 system by Artinis in conjunction with video recordings and eye tracking for behavioral coding of toddlers. We used 22 channels in total, 11 per hemisphere, covering the temporal parietal hemispheres both sides. And for the cap placement, we use the approach described by Renata earlier on. So we place the cap and the optodes using the 1020 landmarks on the baby's head. And in general, in terms of our perspective on the data collection, we found that having a wearable system with optodes and the device already plugged onto the cap made the participant preparation a little bit easier respect to when you have a conventional lab equipment, NIRS equipment with long wires and long fiber bundles. So in this way, the cap placement was quite quick, and also the instrument being lightweight, everything placed on the head, made it also more maybe tolerable for toddlers, having also basically not having the heavy fiber bundles putting their heads back. So this resulted in good quality fNIRS data. Participants were more comfortable wearing the system, so they could go through the whole experiment up till the end. And also, of course, with toddlers, it can be a little bit easier than dealing with infants. So we could also take our time to optimize our fNIRS signals, maximize the optical coupling, as of course, toddlers have more hair than infants. And this was tolerated by most of our participants for this study. However, some of our kids did not particularly like the chin strap below the cap. For this reason, some of our data sets had more motion artifacts than others. So the cap, if the chin strap is not placed properly, can move more easily. And also the cap placement very often was not optimal, with the cap being tilted or pulled up, and therefore we had to exclude those participants. In terms of the data analysis, we first excluded participants based on first their behavior. So if we didn't have enough trials or enough look-in time, but also on the basis of our fNIRS signals. So if the cap was not placed properly, and if we didn't have enough good channels for each hemisphere. In terms of data preprocessing, we have used the Homer2 software toolbox. And here is a screenshot of our pipeline with our input parameters. So within this pipeline, we have included basically the same steps that we discussed within this webinar up until now. So we first exclude the channels with a low signal to noise ratio, channels that exhibited saturation. We corrected for head movements for motion artifacts, combining the spline method with the wavelet-based method. So the pipeline developed by Renata that she just described. We also checked for the presence of residual artifacts. So in case the motion correction methods did not correct properly all the identified artifacts, and these residual artifacts occurred in close proximity to the stimuli onsets, we removed that trial. We then bandpass filtered the data to remove higher frequency noise and very low trends in the data, converted into concentration changes of oxy and deoxy, and then apply the block averaging method. So averaged our oxy and deoxy signals across our experimental condition blocks. So just a minor comment on the preprocessing steps that we applied. So as I said also at the beginning of the talk, and also what Renata just said, it's very important to look at your data to identify what type of noise or what type of motion do you have. So in our data sets, we typically have both baseline shifts and also fast spikes, as shown here in the raw intensity fNIRS data from one participant. So therefore, we decided that the spline combined with the wavelet method could be a good method to account for both type of spikes of artifacts. So here below, I'm presenting just an example of the corresponding oxyhemoglobin signal in black if I don't apply any correction, any motion artifact correction. And on top, we have the oxyhemoglobin signal where I have applied the spline plus wavelet method. We can see that in correspondence of both the baseline shifts and fast spikes, the method works properly and is able to address both type of noise. All right, so in terms of the results, as I said, we cannot run any group level analysis yet, but I just wanted to show you a little bit our inclusion rates, so how well the system performed, how many participants we had to exclude due to different criteria. So here on this table, you can see on the left our initial sample sizes, so our initial participants number per age group. So basically all our participants agreed to take part in the tasks, so except one. So of course, maybe with toddlers it's easier, but they were all quite compliant and were happy to take part in our task. We did not exclude any participant based on technical issues. For example, we didn't have problems with the fNIRS recordings or with the event triggering or with video recordings, etc. We, however, had to exclude a few babies, a few kids due to the cap displacement. So this happened particularly for those kids who didn't want to wear the chest strap, the chin strap. So in this way, basically the cap was not placed properly accordingly to the 1020 electrode placement system. So the cap was either too high or tilted. So we had to exclude those participants. In terms of exclusion on the basis of fNIRS data, we only excluded one participant who did not meet the criteria for good quality fNIRS data. So this is a very good result, meaning that we can get very good quality data on 3 to 5 years old. So that's good news. And we, however, had to exclude a few based on participants' behavior. But to be honest, this might be related to the cognitive task that we've used. So the social non-social task was basically developed for infants mainly. So it might have not been too interesting for older kids, like 3 and 5 years old, 3 to 5 years old. So some participants got bored and they started to move a little bit more and they wanted to interrupt the experiment. So we ended up with not enough body trials. But in the end, these are our final inclusion rates. So we had 77.8%, 80%, 50% inclusion rates, which we think these are quite good numbers compared to previous infants experiments where the exclusion rates are a little bit higher than this. Looking a little bit more in depth into the fNIRS data. So here I'm showing just the amount of channels that we excluded per toddler per age range. So in blue are the right hemisphere channels, in orange the left hemisphere channels. And you can notice that for older kids, particularly for 5 years old, the exclusion rate of the channel was higher than the 3 years old. And we believe that this could also be related to the cognitive task that was probably not engaging enough for them. So they become fast a little bit easier and they start moving around a little bit more compared to younger kids like the 3 years old that just stood in front of the screen for the whole duration of the task. But however, here in general, we recorded very good quality fNIRS data overall. So here I'm presenting the block averaged hemodynamic response across each age groups. So these are group level results, where red is oxy, blue is deoxyhemoglobin, and in gray you see our task block. So in general, we observe very clean and nice responses with nice oxyhemoglobin increases and anticorrelated deoxygenated hemoglobin decreases, which are like very, very, very nice. And this is true also for the other age groups, like the 4 years old, we still observe very good quality data, and for 5 years old as well. Of course, we could not run any stats so far for insufficient sample size at this stage. So to conclude our webinar, in general, within this study, we found that the exclusion rates are generally a little bit lower than toddlers. And besides the obvious age-related reasons where toddlers are more compliant, we think that also the use of wireless fNIRS helped to make the system a little bit more comfortable and lightweight for the participant. So the participant they were more compliant. Almost all of our participants completed the whole task without complaining. We had better quality fNIRS data with lower motion artifacts, not having very long and heavy fiber bundles. And in this way, we also had lower channel exclusion, so more inclusion based on fNIRS data. However, some of the toddlers did not like the chest strap. So the majority of the participants were excluded due to displacement caused by this reason. But And also, it's very important to design a cognitive task that is engaging enough for older kids. Otherwise, we will get more noise in the data and an increase in the exclusion rates of the fNIRS channels. But in general, our preprocessing pipeline that we extended from infants to toddler data analysis was effective in minimizing the the most important noise components in the data. And in fact, we observe very nice and clean hemodynamic responses with anticorrelated patterns, as we would expect to happen during functional brain activity. Great. So this is the very first slide of our webinar. And we wanted to finish our talk going back to our first slide, where we mentioned what are the open issues at this stage in the fNIRS field related to the lack of standardized analysis procedures, but also lack of methodological details in published papers. So here we have included this pipeline for one of my recent papers that include basically all the various steps that we have quickly covered today. And we suggest a few basic pipelines. In red, we indicate the information and the methods information that we believe should be included in all fNIRS paper to first allow the reader to understand the whole study and the whole procedures properly, but also to allow studies replication. So of course, this flowchart might not be exhaustive and is only a starting point, but we hope that this could guide fNIRS user through all the main stages of a neuroscience experiment with fNIRS. And we also hope that within the next few years, we will keep moving towards a standardization of all these procedures. And thank you for your attention.